Hello, I am at Cloud. I'd like to talk about Rust Analyzer, the experimental project to build a Rust compiler which is a good fit for IDEs. That means that Rust Analyzer is fully incremental, on demand, and is capable of providing at least some completion results as user types. So, without further ado, let's take a look at the code. Cd to the necessary directory, open the code. Obviously, to read the source code of Rust Analyzer, we will be using Rust Analyzer itself. There is also a sort of written transcript of this talk, and if you'd rather read text than listen to me, take a look at these pull requests, which contains a markdown document. Also, keep in mind that today is January 2019, the year of the Blade Runner. If you are watching this video in the future, things might have changed since. Okay, so let's start. The typical command line compiler is a batch tool. You run a compiler, you give it a set of source files, and it produces an output, an executable, or a shared library, or whatever. Rust Analyzer, in contrast, is a long-lived process, a long-lived actor. It is a stateful component analysis which you can apply changes to, and which you can query about certain aspects of Rust code, like, for example, what is the definition of this symbol over there? In code analysis, this like highest level API is represented by two types: analysis host and analysis. So analysis host is like a really tiny API which you apply changes to. You start with creating an empty analysis using default impl, and then you incrementally populate it with source information using the apply change method. The change here is basically the contents of this file is now this string. And the third method of analysis host is analysis, which gets you an analysis structure. And analysis has a ton of methods to actually query useful information about Rust code. For example, it has go to definition. One interesting thing about analysis API is that it is based on source files and spans. For example, the input to go to definition is file position, which is a file and an offset in this file. And the output of go to definition is a so-called navigation target, which again is a file, a span inside a file, and like the icon, the name, but it does not really tells you what kind of the Rust symbol it is. It's like an API which is not really Rust language specific. It talks in terms of the simple code editor, which operates on buffers and files. Okay, so as you can see, this analysis has like a lot of methods. If we select it, it's like, okay, Visual Code does not show me the number of lines selected, but like it's a fairly big API. Okay, so why do we need like two types, analysis host and analysis, and what are exactly the changes? So let's first talk about separation into two types. As you may have noticed, a lot of method on analysis, like a lot of, return cancelable results. This solves a very interesting problem. Suppose like you're inside an IDE and you're trying to highlight all the errors across a project. This obviously takes some time to process. And at the very same time, while you are in the process of analyzing the code, user types something in the editor and asks for completion. The behavior we would like here is to get the completion results as soon as possible. And at the same time, because we already have edited the code, we are not actually interested in the results of the error highlighting pass, because we need to restart it anyway. The source code changed. This observation is what explains the cancelable API. The idea is that when you want to do some kind of analysis, you get your analysis host, you call the analysis method and send this analysis to a separate thread and do background computation there. And at the same time, at the main thread, you are waiting for the changes. When changes come, you just apply changes to the analysis host. Important thing to realize here is that there is only one analysis host. You can't clone it, and applying changes requires a unique access to analysis host. But there may be several outstanding analyses in different threads doing different unrelated things, like, for example, syntax highlighting and reference search or whatever. So when you got these outstanding analysis instances and you get an incoming change, what analysis host does is that it marks each analysis as cancelled. That makes all the pending currently executing queries to short circuit and quickly return an error cancelled. And yeah, probably we should take at the definition of these cancelable results. So yeah, cancelable is basically a result where the error type is cancelled, and cancelled is zero size typed. So basically just a marker that the result should be cancelled. Where we were, yeah. So when we call apply change, we cancel all the pending analysis, all the methods returned cancelled, and then background threads die, and we also call drop on the corresponding analysis structs. As soon as all analysis instances are dead, analysis host proceeds with actually applying change. So basically, when you apply change, you kill all background processes, you apply change in place, and you restart analysis if you would like to. Okay, I think, yeah. Another important thing to talk about now is what is analysis change. In other words, what are the input data to the analysis? So let's take a look at this type. It is basically, I think I need an impl analysis change, impl analysis change. Yeah, here it is. So analysis change is basically a builder for a single transaction of changes, and it doesn't have too many methods actually. So you can change source files by adding a new file, changing an existing file, or remove an existing file. You can add a bunch of new files in one go using a library method. It is not essential, it is basically an optimization for crates.io crates, which are expected to be immutable. And you also can set a crate graph. We'll talk about how files are represented in a moment. Currently, you can think of a file as of something with an integer ID, file ID, a text, and a path to the file. And that's it. The more interesting bit is the crate graph. So Rust code originally consists, of course, of source files, but source files is not part of the model of Rust. The model of Rust, the compilation unit of Rust, is a crate. And crate is really more than a single source file, because, for example, a crate is determined by the active CFG flags, and If you point rustc to the same file, for example, on Windows and on Linux, you actually get different crates because they will have different CFG flags opened. A crate also has dependencies on other crate, and this is what crate graph structure is for. Let's take a look at its definition. So here it stores a direct acyclic graph of crates, where a crate is an instance of a crate. It contains a particular file. It contains CFG flags, which we don't actually support at the moment, but like conceptually they should be here. And it contains a list of dependencies, where each dependency is again a particular instance of a crate and a name which would be written in the external crate declaration if you put one into your source code. Remember that in Rust, and which is a really great feature of the language from an IDE perspective, in Rust crates are anonymous, and you need to explicitly pass all the dependencies and not rely on some kind of like goal path or class path or whatever. So let's go back to the crate graph. One important thing to realize is that there is no restriction that a single file ID must correspond to a single crate. You totally can have different crates which point to the same root file ID but differ in CFG flags or dependencies. And this is a major difference in Rust from other languages like C# and Java, because in Java the source code basically corresponds one-to-one to the semantic model. In Rust, a single source file, a single function in a source file can give rise to several instances in semantic model. For example, if you have like a same crates with different CFG flags twice in your compilation graph, or for example, when you include the same file as a module in two different crates. So, and yeah, this is basically it. So, Rust Analyze internally does not do any I/O at all. All the inputs are explicitly passed as analysis change, and the inputs are basically the source files and the crate graph. Running ahead a little bit, we will get crate graph from Cargo, but it is not exactly the Cargo model. Let's get back to this issue about files. You may have noticed this source root ID argument in the addFile method, and you may have noticed that the path is not like std pathbooth, it's some kind of relative pathbooth, and this is very intentional. So what is the problem with files? The problem is that file systems are horrible. You can't check two paths for equality, for example, because it requires you to do a syscall. The file paths are not required to be UTF-8, and like the core issue here is that while we would like to think about file system as like tree of files, it is like not really a tree. You can have cycles of symlinks, you can have like case sensitive file system and lots of stuff. So in Rust Analyzer, I really want the internal model to be a tree of files with UTF-8 paths, so that I don't have to think about differences between Windows case sensitive and Linux, Windows case insensitive and Linux insensitive file system, etc., etc. Another thing which I would rather not care about in Rust Analyzer is the actual absolute path to the files on disk. What I'm talking about. Suppose your project is in like projects for my project. In theory, moving this project to projects bar my project should not change a thing inside when you compile the project. But if you actually give access to this absolute path to the file, you will be able to observe this foo versus bar difference. And so you need to explicitly write code not to depend on these details. In Rust Analyzer, I'd like to just not have access to this information at all. And this actually gives rise to this concepts of source roots. Let's take a look at a virtual file system abstraction. So VFS is a component which is not part of the core Rust Analyzer, which interacts with external file system and converts this horrible world of ext4 file system into this nice tree of UTF-8 paths. And the data in the file system is organized into a set of source root. So a source root or a VFS root is basically a directory, a contents of a directory on the real file system. So it has this absolute path to the root of the directory, and it optionally has this filter, this source root contains only files with .rs extension. And the contents of the source root is okay here. Yeah, contents of the source root is basically a tree of files with a relative path from the source root to the file and with texts. What we do, we create a source root for each cargo package. And each source root remembers all of the files inside cargo package, but it does not know the path to the source root itself. So this VFS thing knows where it was. The VFS abstraction itself, of course, knows the absolute path to the crate root, but the data we pass to analysis change is only ID of the source root and the relative paths to the file. This also is useful for things like this. In Rust, you can have a module declaration with a path attribute, and this path attribute can point basically anywhere. And this is a problem because you don't know the set of input files to the crate until you actually compile the crate. In Rust Analyzer, I sort of explicitly do not solve this problem. I require the set of files to be known upfront so that all the I/O can be done outside of the Rust Analyzer, and the Rust Analyzer can just know the contents of all files it could potentially need. So this means that in Rust Analyzer, this path wouldn't be resolved. You can, by default, you can only refer via path attribute or via just usual mode statement or the include directive to the files in the same source root, because you can only write a relative path here. Of course, if you really need to refer to another file by absolute path, or you need to refer to a file not from this directory, in theory this is not implemented yet, but it could be implemented. You can explicitly add these extra files to source root, but again, it doesn't break this fundamental assumption that before the compilation, Rust Analyzer knows about all possible files which might be involved. Okay, so this concludes the aside about source roots. Let's actually see how we expose this API to the outside world. We do it via the language server protocol, which lives in a separate crate. The core of the protocol is this event loop, which, well, handles events, and there are a ton of events which we might handle here. First of all, we watch, like not really watch, but watch file system for changes. So one possible event is that like user changed branches and the contents of the files on disk changed. Another source of events is the editor. When the user types something in the editor, the LSP client in the editor sends us notification about, hey, this file has new contents. And yet another source of concurrency here is our background processing. When the client requests, for example, syntax highlighting information, we schedule a background thread to compute the syntax highlighting, which allows us not to block the main loop and to process changes quickly. And when the background thread finishes, it sends the results back to main loop, and all the communication happens on the main loop. Okay, so how do we actually get here in the first place? We do here from the main loop method, and what this method does initially, it creates this crate graph input from the cargo metadata command. So let's just walk through a code here. This method is this function is executed. Too many Kotlin programming for me. Is executed when you start the server, and it knows about the root directory where the editor will start, like the project directory. The first thing we do is we send this root to load workspaces. It's workspace loader. So like it's like something which loads project workspace in the background. And project workspace consists of two parts. First of all, it's the cargo workspace with all crates from crates.io and with local crates, and it is also the sysroot, the crates like standard library, core, etc. So yeah, how do we create project workspace? First of all, we find cargo toml, then we read cargo metadata, then we read sysroot and return this thing. And keep in mind that this representation is like really cargo-centric, really RAS-C and sysroot-centric, while the data we have in analysis, this crate graph, is completely build system independent. So once we've got that project, we need to lower this cargo project information to analyze a specific format, and this happens inside server world state. So server world state is binds together analysis host and the information which analysis host does not have, specifically the absolute paths to source roots via VFS, and the information about cargo workspaces via this like project workspace struct. Okay, and so this lowering of project workspace to something with which Rust Analyzer can work happens in this new method. So first of all, we create source roots. We create source roots for each package in cargo workspace and for each crate in the sysroot, and we schedule to read recursively the contents of the source root, all of the Rust files here. The results of this like file system scanning will be handled as other modifications in the main loop. Okay, after we've dealt with sysroots, which basically will give us that file ID to relative path to source text mapping. We reconstruct Crave graph. And currently this is somewhat approximate because we don't really handle CFG changes, we don't really handle platform-specific dependencies, and actually I believe we don't quite have enough information from Cargo to reconstruct this precisely, but of course Cargo can always be extended to provide us with this information. Okay, so for each sysroot crate for each sysroot crate we create like Rust Analyzer crate, and for each package in Cargo workspaces we create a Rust Analyzer crate, and we set up dependencies between sysroot crates from sysroot to Cargo crates, and between Cargo crates themselves. This is like terminology confusion because Cargo actually talks not about crates, it talks about packages and targets. And each Cargo package has many targets, like binary target, library target, test targets, example targets, and each target is actually a crate in Rust speak. Like, not really a crate, you really get a crate when you combine target with particular CFG flag. So for example, like cargo build lib and cargo --test lib --no run are would be two different crates from the Rust Analyzer perspective. But yeah, it's probably getting into the weeds. So yeah, after we have created this source graph, we make change with this source graph and apply this change. So here how we are adding the crate graph to the change. Okay, so let's get back to the main loop. Yeah, so we've loaded the workspace, and yeah, currently we load workspace once at the start of the server. Of course, it should be possible to reload workspace later when you, like, for example, add new crates or change your cargo toml or whatever. It's just not implemented yet. And yeah, in the main loop first of all, let's see how we react to changes to the files. So if we get results from background file system scan, we add the results to VFS. And if we get a notification, and this notification is about like change in text documents, we also write this change to the virtual file system. And at the end of the loop turn, we process all the file system changes which we have gotten in this loop turn. And what this basically does is that it builds an analysis change using changes from the file system, like add file, remove file, etc., etc. And eventually we apply this change to the analysis host using like this familiar method. Okay, so how do we handle requests? Well, we first of all receive a request from the client and call an on request method, and this on request method schedules a request to be run on the thread pool. So this world is this server world structure which contains analysis host instance. The snapshot basically gets us an analysis from this analysis host, and we move this analysis to the separate thread. Remember that while this is executing on a separate thread, on the main thread, we can receive a file change notification, which will call apply change method on the analysis, which will cancel the background thread. And we get a cancelled error here and return a content modified error to the editor. And you actually have already seen this. So this is the debug output from Rust Analyzer, and this is what happened when I've just opened the project. The editor started to ask me about code lenses, about code actions, set cursor, etc., etc. At the same time, the Rust Analyzer was actively scanning the source code. So all those requests got cancelled initially, and then after the scanning was completed, the client asked these requests again and got highlighting, etc., etc. So yeah, let's take a look, for example, on something like go to definition. So we receive this, go to definition request and call handle on the background thread, call handle go to definition function. This function first converts the request from a language server protocol specific implementation to Rust Analyzer specific implementation. This basically means mapping file URLs to file IDs. Then it calls a method inside analysis and converts the results back to the language server protocol types and responds with the appropriate response. Okay, I think this concludes the basic walkthrough around API of Rust Analyzer. You have the stateful actor and you have this elaborate cancellation system, and you need to be very careful about not leaking details about like your build system, your absolute file path, etc., inside the analyzer itself, so that analyzer can be a predictable, reliable, pure function. Now, we actually are getting to the interesting bit. What is the implementation of Rust Analyzer? How it managed to solve everything quickly? So, one approach would be to basically maintain the current state of the world, the current state of all inputs in Rust Analyzer, and on every applied change, schedule a compilation, which compiles the whole crate, possibly incrementally, and then serves a request to the client. And this is actually what a current architecture of Rust language server RLS looks like if you squint enough. Unfortunately, such architecture is necessarily slow. Even if you incrementally compile the whole crate or the whole set of crates of your workspace, you are doing a lot of useless work because you see now I have only a single file opened in my editor, and I really don't care at all about all information except information for the lines between 239 and 283. And this really the place where we need this ability to only query a specific subset of the compilation. So how do we do this? The magic source here is the Salsa crate. I wonder if go to definition will work. Nope. This one won't work because it's a re-export, and this here. Okay, so let's, not everything works of course, let's do it the other way. So this is the source code of the dependency from crate.io, Salsa. Salsa is an awesome crate. It allows you to have a database of queries, and it allows you to execute these queries both incrementally and on demand. What this means is that, like, for example, if you have a query A which uses the results of query B, when you apply changes to the inputs, Salsa will be smart enough to recompute the B if it could have been changed by the changes to the inputs, but avoid recomputing the A if the results of recomputing the B actually stays the same. So if you don't know about Salsa already, my explanation probably didn't make this easier for you, so just stop the video and read some documentation about Salsa. Okay, so let's see a concrete example of a Salsa database. Well, no, let's first of all verify that actually all the state which analysis holds is basically this Salsa database, and this is true both for analysis host and for analysis. And now let's take a look at this database. Well, it has a bunch of queries for different things, and probably the most interesting part of the database is input database. Input, it should be somewhere here. It is called input database, isn't it? Oh, so it's not called input database, it's called files database. That's why I haven't found it. So this database describes the whole set of inputs to the Salsa, and it basically corresponds to that analysis change data structure. As you see, the set of inputs is really small. You have files, and each file has a text, a relative path inside a source root, and a source root. A source root has a set of files. Local sysroots is optimization to know which roots corresponds to files inside the current workspace and which roots corresponds to crates from crates.io. And for crates.io we do at one time, well, not really do, but in some parts we do a top-down one-time processing, which will be, and we produce a really compact data structures. Modifying such for the whole crate data structures is costly, so we use more fine-grained data structures for local crates, but for crates.io crates which do not change often, this is a win. So library roots is the complement of local roots, and the crate graph is the familiar crate graph. So yeah, basically everything else is direct consequences of these input data. So the main thing which we get out of this database is the code model API. Remember how I said that analysis operates on spans and files and does not know about Rust specific stuff. So this is the lower level API which I was talking about, which talks about Rust specific contents like crates, modules, structs, enums, etc. And all these types are represented by an IDE and have a bunch of methods which all take a database as an argument and return some other fine-grained information. For example, for module, you can get a scope, and scope defines the set of names defined in this module. So you can imagine how these powers, for example, completion or go to definition, etc., etc. And what the bulk of Rust Analyzer does is that it provides the queries which populate this rich semantic model. So what are we going to talk about next? Yeah, so probably a good thing to talk about now is that specifics of Rust, where a single source file may correspond to several semantic models. And this is something explicitly handled in the Rust analyzer in this source binders infrastructure. So what this source binder infrastructure does is that it takes information about the source code, the actual files which are on disk, like here is like the file ID and the syntax of a particular module node. And it returns a semantic model for this source node, and it does it basically by guessing. So it like picks the first semantic model which corresponds to this source. So this is like a naturally lossy transformation, but it is only called within the IDE code. And so, for example, if you're like running completion inside the function, this function might be present in like several crates. And in the current architecture, you pick a single crate and run completions, compute completions for that. Of course, it will be possible to like return not an option, but like some kind of like iterable iterator where item is a module and like somehow merge the results, but it will be more work, and hopefully we will get a situation where the majority of the crates correspond, where the majority of the source code corresponds only to a single semantic model. So we use option, which is an iterator of 0 or 1 item. Okay, so let's just see how we actually populate this model, how we actually grade module scope, etc., etc. This, of course, starts with a syntax. And yeah, I have syntax database, great. Great thing about Rust is that to parse source code, you don't need to know the semantic model. And by parsing, I mean like literal parsing. I don't mean macro expansion. So that's why the method parse, it's called source file, but it probably should have been called parse, accepts a file ID. It does not know in the context of which crate we are parsing this file, and it returns a source file. And the source file is basically a node in the abstract syntax tree. So I wouldn't talk too much about syntax tree we are using here. It suffices to say that these syntax tree are lossless, and they explicitly represent all the comments and white space, and they have these like parent pointers, and they have offsets together with lengths, and they are immutable and cheap to update, and they are very much inspired by what I've seen in Swift slip syntax, in Roslyn, and in IntelliJ. So just to get a feeling what a syntax tree API looks like, let's take a look at the assists. So assists are well, why should I explain what an assist if I can just give you an example. So this is replace if let with match. What it does is if you have code like this, if let some do this, else do that. Bit assist replaces this if with match, which to my mind looks a little bit cleaner and more symmetric. And this is a purely syntax tree transformation. So here is the code for all these things, like if you see, not too complicated. First, we find an if expression at the current cursor position. So let's take a look how we do it. So this is the assists context. Assists context, can we go to self here? No, we can't go to self here, too bad. Assists, can we go to definition here? Yeah. Assists context contains a source file and basically the range at which the intention was invoked. Great thing about assists is that they are activated in the specific context. For example, here I can add derive because I'm inside the structure, but if I'm like outside the structure, I don't have this intention, which is great. This assist context contains a range and a source file. And okay, I'm lost. We were here and we were studying node and offset. Wait in the sun. Yeah, here it is. Okay, and so first thing which we need to do to replace if with match is that we need to find an if node at the current cursor position. That's what this method does. Let's take a look at the implementation. Yeah, so first of all, we find a leaf node in the syntax tree at this offset, and then we look at the ancestors of this node, and yeah, it's like a great part, a great feature of this API for writing this sort of assist that you do actually have parent pointers, and you have a uniform representation of the syntax tree so that you can get a like syntax node which represents anything, like a struct, a function, a token, etc., etc. And you actually find the node which is an if expression using this cast method. So despite the fact that you have like this uniform representation, you can also switch to a well-typed representation, like an if expression which has a condition, a then branch, an else branch, and in like Roslyn, in Swift, in IntelliJ, this is achieved by using basically inheritance. So you have like basic syntax node interface and all the concrete syntax node like if expression, class declaration, etc., inherit from this interface, and you just use casts. And in Rust, this is like basically some neat magic. It's not trait objects, it's basically just a little bit of transmutes, but they should be safe. If you're interested in, go read the documentation for the Rowan crate, which is actually what powers syntax trees. So I'm back in the weeds again, and we wanted to replace yes, we wanted to replace match with let. So we get an if expression, and we get a condition, we get a pattern, and we get an expression. And you notice that all of this method returns options. So while Rust syntax requires that each expression has a condition and pattern and then branch, the syntax tree I use in Rust Analyzer allows you to omit these things. So let's see this, create a temporary file, and let's view a syntax tree for this file. So yeah, here I've typed fn foo, so it's definitely not a Rust function definition because it misses parameters, it misses return type, but etc., etc. Nevertheless, on the right we see that in the syntax tree we actually have this function definition, and like when we make a complete, syntax errors disappear. While it is incomplete, we get a red squiggly here signifying an error. And so we can write an if expression here, and we see to the right that we have an if expression, and its condition is broken because it's like a block expression and it doesn't have a then and an else branch, but we do know that this is an if expression. And another like great thing about this is that struct foo, trade bar. Despite all of this being incomplete and unfinished, they actually don't break parsing of subsequent stuff. So the trade bar is parsed completely without errors, despite the errors present in the previous files. So yeah, that's another aspect of these syntax trees, is that they allow you to produce partial syntax tree and don't care a lot if some essential bits are missing. Nevertheless, if we are indeed in the if expression, and if this is a fairly complete if expression which has a condition, a pattern, a then block, and an else block, we actually suggest an edit which takes this if-let and transforms it into a match expression. Oh yeah, if and if-let are both represented by the same if-expr data type. Okay, just to give a quick peek at the implementation of the if expression and those mysterious words about transmuting forecasting. If expression internally, and each IST node internally holds the syntax node. And the syntax node is this homogeneous node which has parent, which returns syntax node, first child, last child, next sibling, previous sibling, which all return syntax node. And if expression is a sort of new type around the syntax node. And what this new type adds, it adds a static knowledge that this syntax node indeed represents an if expression. And so casting works, and what's interesting, casting works even between references. You can cast a reference to a syntax node to a reference to an if expression. And that's because we use this transparent wrapper and a tiny bit of unsafe code, which should be safe, but if you actually review this, it would be ungrateful because I'm not that comfortable when writing unsafe code. So, going back to semantic model, what we've actually talked about was how do we get this syntax database? And yeah, this is also a Salsa query, so each file is parsed lazily only when we request the parse tree, and the results are memorized. So you parse each file only once. Well, actually, in theory, what I am trying to do is to make this syntax tree, which are a relatively heavy data structure because we remember all white space and comments, etc., and they're heavy pointer based, to be a really temporary thing in the compiler. Ideally, only the source file opened in the editor should have a syntax tree present in memory. For all of the other files, I would love to lower the syntax tree representation into some kind of packed array representation with indexes and lots of stuff, and just use that. And we actually see a little of this later. So we get this syntax, we get this code model API, and how do we get from syntax to code model? Well, this all starts with building a module tree. Because really every item in Rust is within the context of a particular module, and you really start with building a module tree. There is a Salsa query, which takes a source root and returns a module tree. So ideally, this argument should be not a source root, but a crate, because really Rust builds a module tree for a single crate. For most historical reasons, we built a module tree for all the crates inside a particular source root. The real reason why this is so is just because source root appeared and module tree appeared before we actually had crates. But the intentional reason is that there are files which are not part of any crate. So for example, I don't know, create a full rs file and this full rs file is not part of any crate. However, I do want to get completion, etc., for this file. And the way I do it, it actually creates a sort of like fake crate for these floating files. And ideally, we should also give an error to the user, hey, this file is not part of any crate. Would you like to include it in cargo toml as explicit library or test or whatever? Okay, so let's actually see how module tree query works. So it takes a source root and it creates this internal data structure, which is not a part of the API, which is a module tree. It is pub here, but only for the reason that Salsa actually cannot have private keys and values at the moment. I hope that this will be fixed. So module tree contains a tree of module. As usual, in Rust we want to have parent pointers in our tree, and so we store tree inside the vector, and we use indexes to refer to particular module. And we use an arena for that, and arena basically a vector with a typed index. So each module remembers the mod declaration it originated from. So this link ID is basically mod declaration, this thing. And the mod declaration remembers the module where the declaration is situated, and the module this declaration resolves to. Points to is a vector to account for like resolve errors when you have both foo-rs and foo/mod-rs and whatever we can have in 2018 edition. It's not actually used at the moment, if I remember correctly. So, how do we build a module tree? The naive way to approach this would be to parse each source file, collect child modules, and assemble the tree. The problem with this approach is incrementality. Source trees are really identity based. So if user types a single character in the buffer, like here I typed a space, the whole syntax tree for the file changed because, well, nodes of syntax tree remember parent links, and as like the file as a whole changed, each constituent node must change as well. And that means that if we read syntax directly when reading the module tree, we'll have to recompute module tree upon every modification. And that seems real unfortunate, because what we actually would like to do is we would like to avoid recomputing the module tree as long as user types something benign like fn do whatever. We only need to recompute module tree when user types mod something, or when they move files around or rename them, or etc. etc. And we achieve this by having an intermediate query. Let me see where we actually called this query. Yeah, so okay, it's kind of difficult to start. Okay, so let's start from the middle. The main idea is that we don't actually inspect raw source code. We inspect the result of the submodules. And submodules is a query which takes a source tree and returns a vector of submodules. And submodule is a plain old data which is basically a string name and a declaration and okay, it's hard to tell the things from the middle, and a pointer in the source tree. And okay, let's pretend that it does not have source. It has only name and its declaration. Okay, so if submodule is this simple, then the submodules query is a really nice query, because although when we change the source code, we have to re-execute submodules query because it depends on the source code directly. the results of the submodules query will not be changed because, well, unless you type a mod foo. So again, the input to the query changes, but the output of the submodules query stays the same. That means that all the queries which depend on submodule query, for example, module tree query, do not have to change unless the actual set of submodules changes. In other words, user typed something in the editor, like a space. Salsa figured out that, hey, source code changes, and module tree indirectly depends on the source code. So we probably need to recompute the module tree. But the direct dependencies of the module tree query are submodules query. And Salsa figures out that all submodules queries for all files except this one are already fresh. So it only needs to recompute this single submodule query for the current file. It recomputes it, and it gets the same result. And Salsa realizes, well, so all the submodules are the same. So the module tree must be the same. And it avoids recompution module tree, which is great. So one bit of info about this source item ID. We actually would like to have a link back to the source code where this submodule originated to. And we can use a pointer to the syntax node here. But this will be bad because syntax trees change after every modification, and this means that with this field, the result of submodule query will be changed after every modification, which is bad. We can store, like, for example, a pair of offsets to the source of the module. But this also will be bad because because offsets change when you type something before the offset. So what we store here is a stable identifier of the source item. And the way we get a stable identifier is that we enumerate all the items in the file and store them in an arena, such that each source item gets an index in the arena. And by source item, I mean like real Rust items, like functions, struct, etc., etc. Expressions are not processed here. And what we get as a result is that each item gets a relatively stable ID. The ID changes only when you add new functions, new top-level items. When you type something inside the function body, the ID of a function stays the same. So that means that this field actually does not change that often, and this means that submodule query stays the same, and that module tree query stays the same as well. And yeah, so the actual procedure of recursively building submodule tree is not that interesting. What is interesting is we'll show a test a little bit later, but the point I'm trying to make is that typing like this does not require this module tree to be recomputed, which is great. Okay, so we've got this module tree which give us modules, and each module has now an identity. And with a module tree, we probably can build a name resolution so that we can resolve paths in use items, etc., etc. How do we do this? Well, and here is an interesting problem appears. We need to somehow identify the items inside the module. For the module tree, the way we identify the module is that we collected all the modules into a single vector in some particular order, and we use index in this vector as identity of the module. And this is probably good because the set of modules changes rarely. And when it changes, the ID of the module changes, and all other sorts of stuff which depends on this ID will have to be computed. But usually they stay the same, and so the dependencies stay fresh. Doing the same thing, completing, for example, all the functions from the crate into a single array will be less fortunate because, for example, adding a new function as opposed to adding a new function, adding a new module is a relatively common operation. So the IDs will be invalidated more frequently. And what's more, you actually will have to crawl across all of the functions. But ideally, we would like to avoid even looking at the functions inside some of the implementation which we not use to type check a particular function which is opened in the editor. So we need some other way to identify the function. And we may use location as the identity of the function. So this is, for example, location structure, which describes a particular item inside the module. So it has a source root ID and module ID fields, which uniquely identify the module, and it has this source item ID, which uniquely identifies an item inside the module. And we understand that this def log of a particular function or struct, or for example, of year. So def log of this def log struct itself will not be changed unless we add a new function in this same file. So it is stable, but it is not really great as an ID because ideally we would like to have our IDs to be like just U32 integers. And def log has all sorts of stuff. And you can imagine that if we would like to see a location of an item inside an impl inside something else, we will need to make this def log recursive and store some kind of vector paths in them. And yeah, this does not look, this doesn't look like compact AD, and like storing it in the hash maps and such, it will probably be slow. So ideally we would like to somehow assign just a numeric ID to this location. And we achieve this via location internal pattern. So what location internal does, it keeps a bidirectional mapping, bidirectional append only. This is important, mapping between locations and numeric IDs. Does it have a lock or something like that? Yeah, and basically when you can give it an ID allocation, and it will give you an ID. And if this internal already saw this location, it will give the ID it gave you previously. Otherwise, it will allocate a new ID by pushing this location to a vector and give you this new ID. So yeah, this is how we turn these positional identifiers into U32 integers. And all of the stuff inside Rust Analyzer semantic model is identified by this sort of integral IDs. Okay, so now we know all the things to look into the name resolution. Name resolution used here in a pretty narrow sense. It only resolves use paths. So it builds a thing called item map, which for each module tells which items are visible in this module. And an item is visible inside the module if it is declared inside the module or if it is imported inside the module. And the idea for building item map is pretty much the same pretty much the same as for building module tree. We can't depend on the source code directly because this will invalidate module item map after every change. So we first lower module into a position independent representation, and then using this position independent representation, which is basically like submodules for module tree, we run this fixed point iterative algorithm resolving everything. And what we get here is basically this test, that typing inside the function does not invalidate item map. So how does this test work? We have a bunch of files here, lib.rs, foo.mod.rs, foo.bar.rs. And we compute item map for this crate. And then we change lib.rs file, and we change the body of the foo item, foo function from like 1 + 1 to 92. And this actually does not re-execute this item map query, and it shouldn't, because we only change the body of the item. The set of items visible in the modules is the same, and that means that like we can speedily give you completions because we know what items are visible about you computing them. So let's look at this lowered module thing. Again, it contains these position-independent items with like names, this position-independent pointer in the source code, and it also contains import. And the import bit is interesting. Why it is interesting? For an obscure reason, when we run completion, if we like complete a foo struct, we need to know if this foo struct was imported, and we need to know a particular segment of the use path which imported this struct. The naive way to do this would be to just like add like something like syntax node to this import, to this lowered import. But again, this won't work because syntax tree changes after every modification, and we really want that test to work. So we use another interesting Salsa parsing here, source map. First of all, again, we store imports inside an arena, so each import gets an ID. And when we use a lower module query, which takes the source of a module and produces this position-independent lowered representation, we actually return 2 bits of information: this lowered module struct and this import source map. And the import source map is bad from the Salsa perspective because it stores, local syntax pair is basically a text range inside the file, so it changes with modification. And so this is like sort of basically a syntax node itself, albeit using a little bit less memory. So this again changes with every modification, and this means that the results of this lower module query also change after every modification. But it actually does the trick because in lowered module we have an import ID, and we can use import ID to look up the syntax in this import source map. However, we want to get rid of this aspect of becoming stale after edit. And this is what a lower module query does. It's a really simple query. It runs that previous query, which returns a pair and projects the first component of the pair out of it. So it projects just lowered module struct. And this query will not change when you edit files unless you actually create a new top-level function or a new trait or something like that. And that's what we actually use here. So again, we want 2 things. First of all, we want to map from semantic model back to the syntax, but we want to keep semantic model independent of the underlying syntax. And we do this by keeping mapping from semantic model to the syntax as a separate source map, and by just removing this source map from the analysis. Okay, so how do the actual name resolution works? Let's take a quick look. Yeah, it's the work of the resolver. So it's this like fixed point iterative algorithm which just iterates over the set of items until all imports are resolved or until it can't resolve more imports. I actually don't know how this works in Rust, and it's actually like a pretty important problem to solve in IDEs, like to implement this name resolution, which should be interleaved with macro expansion correctly. And for that, we probably need the specification first. Okay, so what I'd like to show here is also, the place where we assign the IDs. If you look at the item map struct, which stores for each module a set of item which implemented for it, where each item is basically a def ID accounting for like types, macros, and various namespaces. So we need this def ID, and this is the place where we get this def ID. We get an item from this lowered module, and we know the source root, we know the module, and we know the ID of the item source, so we can create a def log, and we can use location turn inside the database to turn this location into identity. Actually, this code probably does belong to this lowering step. It's here for historical reasons. Okay, so here's how we do name resolution. What else should we discuss? We probably should discuss type inference. Type inference uses all the same patterns, using position-dependent representation, using a source map, being incremental. It is the entry point to type inference. And by the way, a huge shout out to Flodiebold, who actually implemented all of these type inference stuff. So, Infer. Infer runs type inference for a single function. And what it creates a mapping from expressions to their types. And again, what is an expression? If we use the syntax of the expression, we will get query, which will be invalidated every time, etc., etc. So we actually run an extra step before type inference. We lower the raw syntax of function, which contains offset and is not stable, into this compact representation of arena-based IST. So here, expr is not a syntax tree; it's just like your usual recursive enum, except that it uses IDs and not boxes to avoid infinite recursive size problem. And primarily not to avoid this size problem, but to actually give an identity to each expression. And this expr ID is what we store in inference result. Okay, so and again, this uses this source map pattern. When we lower function body, first of all, we get this body struct, which is position independent and contains IDs, and IDs are function local. So if you move function around or move it to completely unrelated file, the body of the function will stay the same. But together with this body, we store syntax mapping, which maps syntax nodes to expressions and expressions back to syntax nodes. And we use these heavily in the IDE. And the actual type inference happens in TI module, and so this is probably the entry point, and this is usual type inference, which works on this ADT enums, nested enums expression representation, and it's like really challenging and really interesting from like type inference perspective. But from IDE point, the core feature which we want from type inference is that we run it for a single function at a time. So to compute completion, we only type check a single function where completion is requested. Why it has taken so long to compute completion? Probably something. Oh, looks like there is some bug in type inference which panics. Well, it's a demo. Okay, so the main thing which we want from type inference is that it works locally to a function. So when we want to run completion, we run it for a single function only, and we actually get this. Okay, so what should we discuss next? Well, probably we have discussed everything. So let's just look at a single feature from the protocol back to the analyzer, to the Salsa database, and back to the analyzer, and back to the protocol. And let's pick completion for this feature. So let's see what happens when you type something in the editor and press Ctrl spacebar to request completion. This starts in the main loop where we get this, how handy, where we get this completion request. That gets routed to handle completion function. Handle completion function converts LSP requests to file position, which basically is a file ID and an offset. This code is like a special case because we want to show completion automatically after you've typed a colon, but we don't want to but we don't want to show completion after you typed only one dot. So we need to check that the previous char is also a column. So not important at all. Okay, so we got our position and we run completion. We get file position and we ask completions on the database. Why this is not using with database, I don't know. Catch cancelled, it's like an interesting side bit in that inside Salsa, cancellation actually is implemented via unwinding. So we literally panic when something types something into the editor while the completion is running, and that tears down all the queries, and here we catch this panic and turn it into a handy cancelable, which is a result. Okay, so what is completions? This is finally the guts of the code completion, where we start to do some useful work. It receives the database and it receives the position in the source file, and it needs to return a set of completions. The first thing we do here is that we figure completion context. So we need to understand, is the cursor after a dot or is the cursor after a double, a colon, etc., etc. Let's see how we do it. Completion context is like a pretty fat data structure. It contains all sorts of interesting bits of information. And so like the basic stuff is like the reference to the database, the offset where the completion was invoked, the leave syntax node where the completion was invoked, so it's like a token, like an identifier or white space or whatnot. It also contains references to the syntax nodes around the insertion point. So for example, if you invoke completion inside the function definition, you will have function syntax. If you invoke completion inside of useItem, you will get useItem syntax. And it also got a semantic model of a function. So remember, there is no bijection between syntax and semantic model. And completion engine must guess the semantic model, and we'll just see how it happens. So yeah, first of all, we need to figure out in the context of which module we are operating. And this goes via that source binder infrastructure, which tries to guess the module. And the way it does it, well, first of all, it determines if we are inside an inline module. The common case is that we are not, we are like just unusual file. And here we construct module from a file, and this means that we just traverse the whole module tree, like we traverse all the modules we know about, and we find a module which originated, the first module which originated from this source file, but there are maybe many modules which originated from a single source file. Okay, so yeah, and this is like one of the most interesting bits, because this is here where we get from the purely source code based representation to the representation where we know the whole context, the crate, the CFG flags, etc., etc. Okay, so now once we have a module, we can fill a little bit more of a context. And the neat trick we do here, which I've learned from IntelliJ, is that to learn the syntax at the current position, we first of all insert a dummy identifier where the cursor is, so that we get a somewhat more reasonable parse tree. And we can, so like, to give an example, if you type something like this, and cursor is here, you like know that this is an identifier and we are supposed to complete an identifier. If, however, there is no identifier at all, it becomes much less cumbersome to understand the context at the cursor, because, well, you don't have an identifier you want to complete. So we insert some random string here and it works. Okay, so if we find a reference in this identifier, we try to figure out what kind of the reference it is. So it probably is inside the function, so we try to find the function outside our cursor position. It also can be inside the use tree, so we find that as well. If we are inside the function, we try to find a semantic model for this function, and this is now much easier than finding the semantic model for the module, because we already know the module, and the module completely determines the semantic context. The create set of CFG flags, so finding the function is basically just iterating through items described in the module and picking the one with the corresponding source tree. So, etc., etc. An interesting bit here. Yeah. If we are a field expression, we also field this dot receiver. Dot receiver is a thing which is expression to the left of the dot. So if we request completion here, the receiver will be this expression. Okay, so here completion, yeah. So we collected the context, which contains both syntactic and semantic information. And now we run a series of completion utilities which fill the context with possible completion variants. And let's look at complete dot, which completes stuff after the dot. First of all, it tries to extract the function semantic model and the receiver's syntax. If there is no receiver syntax, we probably can't complete after the dot, so we just return. Then, given the function semantic model, we run type inference on this function. And we get back a result which maps expression IDs to inference results. But we don't have an expression ID because receiver here, do we have a hover here? No, we don't have a hover here. Yeah, okay. Type inference is not yet perfect. Okay, so receiver is a syntax, and we want syntax ID. So we ask for a source map for the body of the function and look up expression ID using this syntax. Now we can get the actual type because we know the expression ID, and we can complete methods. And like here it is another bit from the context. If we complete in foobar, we shouldn't suggest methods because we know that this is a method call. However, if we complete in just bar, we should suggest both fields and methods. And yeah, here we basically iterate the fields on the type, and we iterate available impulse and suggest completion variants. I think this is almost everything I wanted to talk about. Probably, yeah, a single bit which is missing is macro support. I missed it just because there is not too much macro support in Rust Analyzer currently. Basically, we have a set of hard-coded macros, but it's interesting how it fits into this IDEs infrastructure. So I will tell about it now. The problem with macros is that they effectively create new files. So if you have something not foo and like cfg if std, I don't know how cfg if, okay, some random expression, how cfg if macro actually works. I don't remember the syntax, but I don't know. Yeah, something here. This actually gets expanded to basically a separate file. So we can't say that like the results of macro expansion are in this same sort file, because at least they depend on the current module, because cfg if may be defined differently depending on your CFGs. So we need to somehow handle this. And by handle this, I mean that we use pointers to items everywhere. And naively, we can store a pointer to an item by using a module ID to identify the semantic context, the file ID to identify the file, and the ID of an item inside this file. But this does not work for macro-generated files because we don't have a file ID. So what we do instead is that we use so-called here file ID throughout the core of Rust Analyzer. And this file ID, like, it's pretty natural. It is either the ID of the original source file, or it is the ID of the file generated by a macro. And to assign an ID to the file generated by the macro, we just assign the ID to the particular macro call expression. Macro call goes via this familiar internal infrastructure where we have macro location and macro call. And macro location is simple. We have a module ID to define, again, semantic context, and we get a file where this macro call happens, and we get like the index of this macro invocation in this file, which is again stable across the parsers, blah 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 blah. So yeah, again, a file is either a source file or a macro file, where a macro file is determined by the macro invocation, and macro invocation is determined by the file and the position in this file. And you really see how this is recursive. So again, like, to really see the recursion, we have this file ID. And this file ID stores macro call ID, which is identical to macro log, which stores a source file item ID, which stores a file ID, which is again here file ID from which we have started. And yeah, the point here is that this actually works because this recursion is not infinite. Each here file ID always ends in like the usual file ID, and we actually can see this recursion here. So yeah, to get the original file of the file ID, we check that if we adjust original file, like original file means the file written by the user, we return this ID. If we are generated from the macro, we see the file where the macro call is situated, and we recursively return original file ID of that file. Okay, so do we have a macro database? No, we don't have a macro database. So this is like how I imagine macro expansion can be implemented. You have this potentially macro file ID, and then you have expand macro invocation query, which looks at the source syntax, resolves the macro invocation to macro definition and macro input, where macro input is just a token tree, and like parses this macro input back into the syntax. And to get the code of macro expansion, you again either look up the original source file, which you get from the parser of the file on the disk, or if it is a macro, you expand macro invocation, which again can be recursive because Salsa allows recursive queries, and you return the syntax tree for that macro expansion. Actually implementing macro expansion is of course future work. Okay, so I think this is definitely it. It was longer than I expected, but I hope it was interesting. Okay, bye. Actually, bye.